This is a G485 revision video for chapters 12, 13 and 14, the atomic structure, nuclear physics and radioactivity. We'll start off by looking at the alpha scattering experiment. We need to know what is in the experiment and the conclusions drawn from this. These are: the nucleus is tiny because most alpha particles are not deflected or deflected very little. The nucleus is positive as some particles are sent back the way they came, they are repelled. And the nucleus is where the bulk of the mass is. This is because the alpha particles came out with the same energy they went in with.
Inside the nucleus there are protons with a positive charge and neutrons with no charge. Together these are called nucleons. The number of these nucleons is the nucleon number A, and the number of protons is called the proton number Z. X is the chemical symbol of the atom. The proton number defines which element you have. Isotopes are a different version of the same element, but they have the same Z but different A, and in that they have the same number of protons but different numbers of neutrons.
In the atom, you need to know the different sizes and forces. The radius of the proton and neutron is 10 to the minus 15 metres. The radius of the nucleus is 10 to the minus 15 metres to 10 to the minus 14 metres. The radius of the atom is 10 to the minus 10 metres. The size of a molecule is 10 to the minus 10 to 10 to the minus 6 metres. The atom is at least 10,000 times the size of the nucleus. You also need to know the forces. Inside the nucleus is a strong nuclear force. It's experienced by neutrons and protons and is very short range and attractive. There are three different types of nuclear decay equations: alpha decay, beta decay and gamma emission. In alpha decay, 2 protons and 2 neutrons leave the atom. In beta decay, a neutron turns into a proton and an electron is emitted. In gamma emission, there's normally too much energy, so a photon of electromagnetic radiation is released. This is ionising. For alpha it is strongly, beta moderately and gamma weakly. Alpha is stopped by paper and a few centimetres of air, beta is stopped by a few millimetres of aluminium, and gamma is reduced by a few centimetres or several metres of concrete. Matter is made up of hadrons and leptons. Leptons are fundamental. Examples are electrons, neutrinos, positrons and antineutrinos. Hadrons are not fundamental and are made up of quarks. These experience a strong nuclear force. It is separated into 2 groups, mesons and baryons. Mesons are made up of 2 quarks, a quark and antiquark, and baryons made up of 3 quarks. Examples of mesons are kaons and pions. Baryons examples are neutrons and protons. We need to know the different types of quarks, their symbol, charge, baryon number and strangeness. The quark model is also extended to include more quarks, which are the charm, bottom and top quarks. They have properties of charm, bottomness and topness. A neutron is made up of an up quark and down quark. A proton is made of up, down. Charge and baryon number are always conserved. Strangeness can be changed in interactions involving the weak interaction. Quarks can also change their flavour if the weak interaction is involved, for example in beta decay.
Neutrinos and antineutrinos are released in beta decay. During interactions involving beta decay, it was discovered that the electrons were leaving with a range of speeds, which would indicate that there is another particle carrying off some of the energy and momentum. This, in normal beta decay, it's the antineutrino, and is the normal neutrino in beta plus decay, which is a positron.
Quarks experience a weak interaction. This is responsible for beta decay. Beta minus is an electron. Beta plus is a positron. It should be called the anti-electron. There's also a neutrino and antineutrino involved. Here we have an example of an exam question that could be used. State the difference between each of the isotopes shown in the table. These always have a different number of neutrons, but same number of protons. The structure of the proton in terms of up and down quarks is up, down. Describe what happens in a beta plus decay using a quark model. Up goes to down, plus a positron, plus a neutrino. The 2 quantities conserved in beta decay, for example, are charge and momentum. Examine the table of isotopes in figure 5.1 and suggest what determines whether an isotope emits a beta plus or beta minus. Beta plus is emitted when there are fewer neutrons.
It takes energy to pull apart an atom. This energy is called the binding energy. The larger the binding energy per nucleon, the more stable the atom. You can calculate this by comparing the mass of the atom to the mass of the protons, neutrons, and electrons that make it up, using delta E equals delta mc squared. Binding energy is the definition of binding energy is the minimum energy required to separate the nucleons in a nucleus. The definition of the binding energy per nucleon is the minimum energy to separate the nucleons in a nucleus divided by the number of nucleons. Nuclei become more stable as binding energy per nucleon increases. As you can see by this graph, Fe56 here, iron, is the most stable nucleus requiring the most energy to break. Lighter nuclei tend to have low binding energies per nucleon. Helium is the most anomalous point on this graph because it is an alpha particle and is very stable. The nuclei heavier than iron have a less steep line than the nuclei lighter than iron. So this is a worked example using the E equals mc squared equation from above. So in this you have to calculate the binding energy per nucleon for the 56 Fe nuclide. You have the mass of a neutron, the mass of a proton, and the mass of the whole nucleus. So the mass defect is the number of protons and neutrons, the mass of the protons and neutrons minus the mass of the nucleus itself, which gets that value. That value then needs to be put into the delta mc squared, c being the speed of light squared, to determine the binding energy, and the binding energy per nucleon is the binding energy divided by the number of nucleons. And it also gives it in electron volts. Fission occurs when a large nucleus splits into two medium-sized nuclei. This usually happens when a neutron is absorbed and results in the emission of more neutrons that go on to cause other fissions, hence that cause a chain reaction. Reaction is used in nuclear power stations and in certain bombs. The products are radioactive, inevitably. Fusion is when the smaller nuclei are pushed together to form larger nuclei. The fusion releases more energy per nucleon than fission as the slope is steeper. So the reaction in stars and hydrogen bombs. It can be done with isotopes of hydrogen found in water, and the products are safe, but it cannot yet be done on a commercial scale. This is a repeat of the binding energy per nucleon graph, but it's showing that the heavy nuclei need fission because the binding energy needs to increase. So the heavy nuclei have to be done for fission, and the lighter nuclei have to be used for fusion. And again, the slope is much steeper, so fusion releases more energy. Power stations use induced nuclear fission, which is firing neutrons at large and stable nuclei, usually uranium-235, which the neutron is then absorbed, causing the nuclei to split into lighter nuclei and more neutrons. An example of an induced fission reaction is here, involving uranium-235, which absorbs the neutron, turning it into uranium-236, which then splits into its products and more neutrons. The neutrons hit more nuclei, which causes a chain reaction. To maximize the chance of this, the neutrons have to be slowed down, which are called thermal neutrons. Nuclear fusion is not used commercially because of the high temperature and high density needed, because it needs similar conditions to those in the Sun. This is inside the core of a nuclear reactor used in nuclear fission. The control rods are made from a neutron-absorbing material, for example boron, which are raised and lowered to control the rate of reaction. Raising it speeds it up, and lowering them slows it down. The coolant is usually made up of carbon dioxide gas, although it can be made out of pressurized water and other coolants, and is used to take the heat out of the reactor, which goes on to heat the water, which goes on to turn the turbine. It is not the coolant, because the water that is used to turn the turbine is not the coolant, because if the coolant was used, it could be contaminated with radioactive material. The moderator, which is usually graphite, is there to slow down the neutrons, because the neutrons make inelastic conditions which take some of their energy away, which turns them into thermal neutrons. The fuel rods are made out of fission material, uranium-235, which is what undergoes fission. After the fission occurs, lots of radioactive products are left behind, requiring them to be disposed of, deep underground or in monitorable containers on the surface. So this is an example of an exam question from the June 2013 paper. This shows a graph of binding energy per nucleon, which is roughly similar to the graph seen earlier in the video. The first question is to use that graph to estimate the value of the nucleon number of the most stable isotope. It accepts from 50 to 70, which is roughly around here where it is. Anywhere in that sort of gap will be acceptable for the answer. You also need to use that. For the next question, you need to use that graph to explain why the 100 MO nuclei cannot produce energy by fusion, because the binding energy will decrease, as seen here, which meaning energy will be put in, which means you won't gain any energy. The third question, the mass of a 8Be nucleus is 1.329 times 10 to the minus 26. Use the data provided on the second page of the formula booklet to determine the binding energy per nucleon for this nucleus. So first you need to figure out the total mass of the nucleus, which is again we're doing 4 times by the mass of the neutron plus 4 times by the mass of the protons. The change in M is that mass minus the mass of the nucleus overall, which is in the question, and the mass that equals a mass defect, which is that number there. The binding energy overall is AE equals mc squared, which is the mass defect times by the speed of light squared. For per nucleon, you must divide that by the number of nucleons, which gets you to a final answer of 1.148 times 10 to the minus 12.
For the next chapter, we look at radioactivity. We need to know the definitions of decay and random. Decay is spontaneous. It cannot be predicted. Random is the rate is constantly varying. The number of unstable nuclei in a sample is n. The probability that a single nucleus will decay per unit time is the decay constant. The amount of decays in a sample per second is the activity. If you have enough nuclei, A can be approximated as equal to lambda n. When measuring decay, we measure the count rate, R, which is calculated by subtracting the background radiation. It is lower than but proportional to A. The time for n to drop to a half of its current value is constant. It's known as the half-life. The rate of decay drops as the number of undecayed atoms drop. Here's an example of the decay graph. It's an exponential curve, and the equation n equals n0 e to the power of minus lambda t is used. Here is a worked example. You're given most of the figures and you just sub it into the equation to find the answer.
From the previous equations, we can discover the relationship between half-life and the decay constant. So by using the equation for the number of undecayed nuclei, we can use n, which is n equals n0 e to the power of minus lambda t. Then we rearrange it to get n over n naught equals e to the minus lambda t. When t is the time of the half-life, n over n naught must be 1/2 because n naught must be twice of n. This means that a half is equal to e to the minus lambda half-life. Then we take natural logs of both sides. Natural log of a half would get natural log of e to the x gets to x, so it's natural log of a half equals minus lambda half-life. Lambda times by the half-life is the natural log of 2, which is 0.693. Carbon dating is used to measure how long since an organism has died. All organisms take in and give out carbon atoms, some of which is carbon-14. The fraction of carbon-14 atoms is roughly constant until the organism dies, when it's no longer taken in, so it decays. The half-life of carbon-14 is 5,730 plus or minus 40 years. By measuring the fraction of carbon-14, the time since death can be measured. The issues involve recently dead organisms have little change in the fraction of carbon-14. There is less carbon-14 in the atmosphere today due to fossil burning than there used to be, so it's difficult to measure it compared to today's fraction. An extremely small amount of carbon-14 atoms in any given amount. There is 1 in 10 to the 12 atoms, so there's a very small count rate, and there's the small uncertainty in the half-life. Because of this, mass spectrometry is used today due to the accuracy and sensitivity.